הוא מוקדש לפוטנציאל והחשיבות של מחקרי אורך בתחום החינוך. במושב יש לנו 3 הרצאות, האחת היא הרצאה של, אולי אני אתחיל, של פרופסור דיוויד קפלן מאוניברסיטת מדיסון-וויסקונסין, על הזדמנויות ואתגרים באיסוף וניתוח של נתוני אורך בחינוך. ההרצאה השנייה היא של פרופסור משה יוסטמן, על הפוטנציאל של מחקרי אורך בתחום החינוך בישראל, וההרצאה השלישית היא של פרופסור ויקטור לוי, שידגים לנו באמצעות 4 דוגמאות על ההשפעות ארוכות הטווח של התערבויות חינוכיות בבתי ספר יסודיים ותיכוניים בישראל. תהיה לי ההזדמנות לומר גם כמה מילים על כל אחד מהמציגים, ואני אתחיל עם ההרצאה הראשונה, וברשותכם אני אציג את פרופסור דיוויד קפלן, ואני אעבור לאנגלית לכמה משפטים. Professor David Kaplan is the Patricia Bast Professor of Quantitative Methods of the Department of Educational Psychology at the University of Wisconsin-Madison. Professor Kaplan holds 2 additional affiliate appointments in the University of Wisconsin, in the Department of Population Health Sciences, and in the Center of Demography and Ecology. He is also an honorary research fellow in the Department of Education at University of Oxford. He is an elected member of the National Academy of Education and a fellow of the American Psychological Association. His research focuses on the development of Bayesian methods applied to a wide range of education research settings. Since 2004, he has been actively involved in the OECD program for International Student Assessment, PISA. He served as the chair of the questionnaire expert group for PISA 2015 and remains a member of this group for PISA 2018. He also participates in the questionnaire expert group for the OECD Teaching and Learning International Survey, TALIS. David, we greatly appreciate your immediate response to our invitation, and I have the pleasure to invite you to give your talk. Please, the floor is yours.
Thank you. Shalom v'boker tov. I want to first begin by thanking Leah and Oded and Avital for the wonderful invitation to be here. I've been to Israel many times before, but I always very much enjoy coming back and look forward to this meeting. I look forward to what I have to say and look forward to any questions that you might have. So let's get right to it because I have a fair amount that I want to cover. First of all, I'm going to shamelessly reference myself here in terms of where I'm drawing most of my material for this particular talk. I believe the slides for this presentation will be available to everybody, so in the event that you wish to have any of these papers, simply contact me and I'm happy to send them to you. So we're going to talk about opportunities and challenges, what we call back home in Wisconsin, chopportunities, challenges and opportunities. We're going to go with the opportunities first of using longitudinal data for policy analysis. And I'm going to do this in a very non-technical fashion, as non-technical as I can possibly be, by indicating what are some of the advantages of collecting longitudinal data in terms of the kinds of statistical analyses that one can employ that answer questions in a very deep way with the use of longitudinal data, whether that's longitudinal data collected in perhaps the way you would want to collect it, which is by looking long-term, launching a longitudinal study, or even if you happen to have administrative data that you wish to use, there's a considerably rich amount of information that can be brought to bear with longitudinal data and with statistical models that have been developed over the years. So we'll talk about those, and then we'll talk about the challenges in collecting and using longitudinal educational data for policy analysis. And in particular, I'm going to focus my discussion, when we get to it, on the problems of file matching, and I probably will skip over the issues of privacy because that's much more an Israeli context problem than it is a U.S. problem per se. And then I want to close off by discussing some extended opportunities, things that I'm currently interested in that I think can be brought to bear with the use of longitudinal data in education. So let's go ahead and get right started. What I want to do is I want to talk about longitudinal data in the context of a particular longitudinal study in the United States, just to contextualize my remarks. And then you can think about this in terms of the ideal administrative data that one might be able to pull together. So I'm going to focus my attention on the early childhood longitudinal study, the kindergarten cohort of 1998. This is old data already, and in fact there is newer cohorts of data, but this is some of the work that we've done with the ECLSK. It's arguably the most comprehensive survey of the development of the academic competencies, and in fact, now in non-academic competencies over the early elementary and secondary school years. And it's nationally representative of the kindergarten cohort of 1998. So these kids are out of college already, and they're still being followed up to a certain extent. So what is it? From the NCES website, National Center for Education Statistics, the children came from both public and private schools and attended both full-day and part-day kindergarten programs, came from a diverse socioeconomic status and racial and ethnic backgrounds. Also participating in the study were the children's parents, teachers, and schools. So it was already a multi-level structural set of data. Children, their families, their teachers, and their schools provided information on children's cognitive, social, emotional, and physical development, information on children's home environment, home educational activities, school environment, classroom curriculum, and teacher qualifications were also collected. It's a massive survey. The ECLSK followed the same children from kindergarten through the 8th grade, and was designed to provide a comprehensive and reliable database that can be used to describe and to understand better children's development and experiences in the elementary and middle school grades, as well as how children's early experiences relate to their later development, learning, and experiences in school. The data collected across the years allow researchers and policymakers to study how various child, home, classroom, school, and community factors at various points in children's lives relate to their cognitive, social, emotional, and physical development. So to begin to describe some of the advantages to the use and collection of longitudinal data, and in particular kinds of statistical models that can be described and or used or applied to this kind of data, let's start first with an example of just a random sample of 20 trajectories of growth across 4 waves of the ECLSK: fall of kindergarten, spring of kindergarten, fall of 1st grade, and spring of 1st grade. So this is just a sampling of 20, literally a random sample of 20 growth curves. Nothing's particularly special about this. One of the first things that you see when you look at just the trajectories is the just sheer amount of variability in the trajectories that we see. Kids start off different. They grow at quite different rates and not linearly by any stretch of the imagination, quite a lot of disjunctions in their growth. And then they end, if we want to consider the 4th wave as the end of this particular set of curves, they end quite different from each other as well. And in fact, they start off with much lower variability than they end with, presumably, the effects of schooling taking place across those 4 waves of the early childhood study. So we can describe these curves as following sort of 2 levels: intra-individual differences and individual differences. In the case of individual differences, these are what we saw in the graph, namely children starting at different levels, changing at different rates, and ending at different levels. The statistical models that we have available for handling longitudinal data provide an estimate of where they start, some sort of average estimate, some average rate at which they grow. course, we can always consider the possibility of looking at where they end as opposed to where they start. And sometimes for some kinds of growth questions, where they end up is more important, at least on average, than where they started from, especially if they're very, very young children, where you might not see a great deal of variability, therefore very little to explain. We can extend these models to be nonlinear, to take into account the fact that we see very different trajectories. We have a child going up, then going down, then going back up again. We have a child here who's relatively flat in his or her growth over time. But now that we've described the average starting point and the average rate of growth, we notice that there's variability around that, and the variability is what we wish to explain. So we are interested in the predictors of this variability that we see in the growth curves. We can examine the impact of policy-relevant variables on the average starting point and the rate of growth. And these predictors can even be interventions designed to impact these growth parameters, where they start and how fast they grow. Then, of course, all of this could be, in fact, and it is with ECLS, nested within schools that those children happen to be in. That's not the case here. This is just a random sample across the entire survey. But you could imagine a situation where we're interested in the contribution of a school and characteristics of the kids within those schools on the growth rate of those kids over time within those schools. And these can be handled right now quite easily and quite elegantly with the statistical models we have available if you have the right kind of longitudinal data. So what I want to do is do this in the form of diagrams. And first of all, pay no attention to these numbers. I couldn't figure out how to erase them, and they have some kind of technical meaning to them that are not important. But we can conceive of these growth models in the form of what we call path diagrams or directed graphs or whatever you would like to refer to them here. Now, this is actually not the ECLSK. This is another longitudinal study in the United States called the Longitudinal Study of American Youth, where we had 5 waves of some science scores. And all this represents is that we can represent the science scores as basically changing over time as a function of where they start, this initial status, and their rate of change over time. And we allow those two to be correlated because in some sense, where you start, to a certain extent, dictates, if you will, for lack of a better word, how quickly you grow. In terms of the test, it can also indicate whether or not a ceiling has been hit in terms of the difficulty of the test. So this is a very basic diagram, and of course this represents some measurement error because these measures are not necessarily perfect. But we can do more. We can add a predictor of the growth. We can add gender. To look at gender differences in how fast, on where they start and how fast they grow, and allow those two to be correlated still, even having taken into account gender. So having taken into account gender, is there still some residual amount of growth in initial status, in science over time? But we can do more. We can allow for the possibility that in addition to where they start and how fast they grow, certain events take place at each time point that influence whether the curve is up or down at that particular time point, what we call a time-varying variable. In this case, it could be how much the parents press their kids to learn science, how much the teachers press in the school for the kids to learn science. Now, we don't expect that to be the same across each year, and therefore, we imagine them to be varying over time, where we imagine gender to be relatively stable over time, time invariant. We could do more. We can say that in addition to the initial status and the rate of growth, depending on how narrow the time frame is between the waves of the study, wave 5 could also be, the scores that a child gets on wave 5 could be determined partly by the scores they get in wave 4. So there's still some residual taking place here in addition to where they start and how fast they grow, allowing for autocorrelation in addition to rates of growth. All of these are within the current statistical models for handling longitudinal data in a very sophisticated way and allowing one to ask some very deep questions. We can even go further. We can have two processes taking place at the same time that we're interested in. For example, this comes from a study that I did with a colleague back in the States, Nancy Jordan, where we collected actually our own longitudinal data for this. And our interest, or I should say actually her interest really was, the extent to which young children who use their fingers for counting, the extent to which their use of their fingers in some sense predicts their accuracy in number counting over time. So there's two issues here that are interesting. The first is, does the use of their fingers for counting change over time? And as that changes over time, does that simultaneously predict whether accuracy is changing over time? And at what point is it perhaps a good idea to wean children off of the use of their fingers as they're increasing their accuracy in their number counting and number sense? So we can look at sequential growth in several processes, in this case, two processes. This process here allowed for the fact that what we recognized is that the use of fingers took off linearly and then flattened. Kids use them a lot, and then they slow down, whereas accuracy increased only linearly. And therefore, in a model of this sort, you can have processes that are changing differently, in some sense slowing down or speeding up, and in other cases linearly, and allowing there to be connected, and then connected still to some things we might be interested in. Are there gender differences in finger use and accuracy? And in our case, more importantly, were there income differences? Kids from low socioeconomic status levels, we have found, were using their fingers longer, relying on them longer, therefore not developing quick number sense compared to their middle class, if you will, children. All of this, now I don't have a diagram of this, but all of this could be connected to a variable out here that represents what we call a distal outcome, something we're interested in that's beyond the stages of this developmental process later in time, such as a test, a national test of some sort, a final exam in some sort, whatever the policy or research relevance might be. All of this, again, relatively easily handled in existing software, existing statistical models. So, as an example, to give you sort of an actual numerical example, what we're going to go is to return back to the ECLSK. We're utilizing some data from the kindergarten base year. Only first-time public school kindergarten students are chosen for the example. Sampling design of ECLSK actually included a 27% subsample to reduce cost. This was during the fall of first grade. Total sample size was approximately 3,500, and this is just an example. That's what the caveat's for. We looked at the ECLSK reading assessment measure, an indicator of whether the children were in full day versus part day kindergarten, a measure of socioeconomic status, and the child's age of entry into kindergarten. The research questions for this paper were the following. What is the general level and rate of growth in reading proficiency among the sample of ECLSK children? How do the growth rates differ for children attending full day versus part day kindergarten? And does the effect of full day versus part day kindergarten program change when controlling for the age of entry into kindergarten and socioeconomic status? So we're not going to show any actual data, we'll just show some figures as to what you can find. And what we find is that children who are in full day kindergarten without controlling for socioeconomic status and age are not really significantly different from those attending part day without SES and age. Well, they might be significant because there's 3,000 kids in here, but for practical purposes, it's not a really big difference. What happens when we control for socioeconomic status and age? We begin to see sort of a separation which indicates a selection bias into full day kindergarten with respect to socioeconomic status and age of entry into kindergarten. let's return for a moment to the curves again that I showed. And notice that, and this was actually, interestingly enough, completely accidental. This was just a random sample and it turned out to be this way. So what I talked about before is that you notice that there's variability where people start, variability and wider variability, in fact, where people end, and some very distinct looking kinds of shapes. If you look carefully, if you squint your eyes and turn your head, one of the things that you'll see is that, in fact, one could argue that there's actually a kind of a grouping of curves that we see. Some curves here, some kids kind of already coming in knowing quite a bit and growing at a slower rate. Some kids kind of growing at a more moderate rate, and this one child who seems to be having some difficulty across the 4 years. In the growth curve models that I just described, what one would do is fit a single curve to that entire group. What we would call a one-size-fits-all growth curve model. But we might not be interested in doing something like that. Our concern is that we are really observing, or possibly what we're observing, are distinct growth curve shapes. And the implications are, for interventions, very important. Knowing if there are subpopulations with distinct curve shapes we're talking about permits tailored interventions, not a one-size-fits-all intervention, which is perhaps doomed to fail since it's missing the group in some respects that it should be targeting. So we need a method to discern if there are distinct growth trajectories, how many of them exist in the data, and how many individuals can be classified into having these shapes. This is the goal of what we refer to as growth mixture modeling. What we have is a mixture of growth curves, not a single set of growth curves from some population, but rather very distinct growth curves. Growth mixture modeling is a general form of what's called general mixture modeling, and the idea is this: in any given population, there might be mixtures of subpopulations of varying number and size. The general idea is that we can use some statistical models on these subpopulations and then characterize our statistical models by parameters that are unique for those subpopulations. For growth mixture modeling, the subpopulations are characterized by qualitatively, that is to say, perhaps substantively important growth curve shapes. The model parameters represent the shapes of these trajectories within subpopulations. So all this is by way of saying that there are perhaps 3 distinct subpopulations in what we might normally think is just one population. And that if we drew policy or research conclusions on the basis of fitting a one-size-fits-all, we are missing the nuance that we could have if we look to see, from a modeling point of view, how many shapes there are, and how many people are in those shapes. So let's do that now with the same analysis and the same data that I just talked about, the ECLSK. What we found in doing this analysis is that there were in fact three growth curve shapes that were qualitatively different. There was what we called class 1, which had the largest number of individuals in it. That's this group right here in the middle. Kids who start off with relatively low reading scores, but basically develop in a reasonably nice linear fashion. The statistical modeling identified these 3 growth curve shapes. There weren't 2, there weren't 4, there were 3. With 72% of the sample in that particular group. In the meantime, there were kids that showed up that came in fairly high, grew, but because of a ceiling effect in the test, basically had no other place to go but flat from that point on, nonlinear in fact. We called them the fast developing group because we couldn't come up with a better and more clever label for it. So the fast developing group showed up to be about 13% of the population. And then we have kids who are starting off actually at the same point as the quote-unquote normal developing kids, but growing at a much slower rate and in fact don't quite catch up. And that represented 15% of the population. Considering that the ECLS-K was a sample from a population that was not suffering, as far as anybody knew, from any kind of reading disabilities or any major disabilities because of their exclusion criteria for this particular study, this ends up, according to the experts that I consulted, about what you would expect in a quote-unquote normal population. Okay, so this had some validity to it. This could only be determined if we allowed for the possibility that there are distinct growth shapes. So now the question is, what is the relationship between between full day and part day kindergarten within these growth curve shapes? In other words, does full day kindergarten or part day kindergarten confer any advantage for kids who are in these different groups, as opposed to assuming just one group? And it's a little hard to read, but basically what we find is that if you are already in this high-performing group, being in part day or full day kindergarten really does not make it much of a difference. Similarly, what it does appear is that the normal developing group, and you'll forgive those labels because they're not really accurate, the normal developing group seems to not be much different either, although those that are in full day kindergarten do a little bit better than those that are in part day kindergarten. But interestingly enough, what you do see is that the kids who are in part day kindergarten who are growing at a slow rate continue to do so, but those kids that are in full day kindergarten, and that's the diamond right here, who are in full day kindergarten seem to be growing at a much greater rate, indicating that full day kindergarten and part day kindergarten might in fact have a beneficial effect for kids who are in a slow developing, for lack of a better term, a slow developing trajectory. Aha.
A clarification, the last group that you talked about, they did not start as low as the previous one.
That's right.
So could you explain?
Which group? I'm sorry.
I thought that the difference, yeah, the lowest were the kids who started low and continued developing slowly.
That's this group right here.
They were in a part-time.
But now what I'm doing is I'm separating them out.
Yeah.
These folks are in the part day kindergarten. These children are in part day kindergarten. These children, is that a diamond? Yeah. These children are in full day.
But the starting point is not the same.
No, it's not. Because they're now separated within their trajectory class.
Okay.
They're separated within their trajectory class. So we see that these kids are even slower, right? So one might say that this is, and flatter, incidentally, than the kids that are in the diamond class, for lack of a better term. However, the story is not over because we have not controlled for socioeconomic status and age of entry into kindergarten. When we do, that's what we get. Everything seems to disappear. Most of the effects seem to disappear. So in tailoring an intervention, what we learn is what happens when we control for some of the non-random selection into these kinds of programs. And that age of entry into kindergarten turns out to be a fairly important predictor. But the point of this is not these specific results per se, but what can be learned if you allow for these growth trajectories to possibly be qualitatively different from each other. You would not know this if you had simply fit a one-size-fits-all curve to everybody. And that's the idea behind what I'm trying to point out today is what can be learned with the methodologies that currently exist if you have the right kind of longitudinal data. Okay, so what we talked about was change in discrete time. Let me go through. Change in discrete time with an outcome that's continuous, namely a reading score. But that's not the only way we can conceive of growth or change. We can think of growth and change as growth and change in states, in categorical change over time. And to give examples of this, from psychological literature are Piaget's stages of development or Kohlberg's stages of moral development. These are not changes in some continuous outcome over time. These are qualitatively different moves from one state of being to another state of being. Well, it turns out that the ECLS-K provides measures that can be used to test hypotheses regarding stage sequential development in reading competencies. And there's been some prior work on this topic, and we are the first, my colleague Sharon Walpole and I, were the first to try to do this in the context of reading using a much larger national database. So the ECLS-K provides transformations of continuous scores into probabilities of proficiency, as well as dichotomous proficiency scores, which is what we used. What they do is they design a cluster of reading assessment items that have similar content and difficulty. Then a child is assumed to have passed a particular skill level if he or she answered at least 3 out of 4 of the items in that skill cluster correctly. A fail score is given if the child incorrectly answers or did not know at least 2 items within the skill cluster. So now you essentially have mastery or non-mastery of a skill cluster within reading over time. And the question then is, are children moving from these categorical mastery states into further categorical mastery states as they go through time? So we did this. The measures we use consist of a series of reading assessments designed to measure basic skills that have been identified as particularly salient in the first 2 years of schooling. The reading assessment uses what are called Markov chain models for developmental processes, letter recognition, beginning sounds, ending sounds, sight words, and words in context. Let me go ahead and skip past this and take you to the results of this. This is one of the things that you can learn. I'm sorry.
It's very optimistic to think that we see.
They don't see the table.
Oh, yeah, I'm sorry about that. It's also, I can't see it either. So I'm just making it up. Yeah, I mean, I can't make it any larger, I don't think. But the basic idea that what you see here is that in the fall of kindergarten, we have identified 3 clusters of skill. Low alphabetic knowledge, early word recognition, and early reading comprehension. And then over here are the subtests: letter recognition, beginning sounds, ending sounds, sight words, and words in context. We named this group low alphabetic knowledge because 47% of the sample mastered letter recognition, but a very, very small probability of the sample mastered anything higher than that. And that constituted 67% of the sample. In early word recognition, 97% of the kids mastered letter recognition, 87% of the kids mastered beginning sounds, 47% mastered ending sounds, but very little else. However, when you move to spring of kindergarten, then fall of first grade, and spring of first grade, you will notice that the percentages of these kids start to change over time. And the reason for this is that the children who are in this stage of low alphabetic knowledge within the fall of kindergarten should be progressing into higher levels over time. The question is, are they, and by how much? These are what are referred to as transition probabilities. So in the fall of kindergarten, the probability that a child who is in a low alphabetic knowledge class staying in that low alphabetic knowledge class is 0.3. But the probability of that child moving is 0.69 to the next class. And similarly, very low to go to the further class in the spring of kindergarten. But if we go to the spring of kindergarten, moving to the fall of first grade, we see that those in the low alphabetic knowledge, there is still a rather high proportion of kids that are not moving. And yet 40% are moving, again 1% are not. And we begin to see the similar idea along the lines of early word recognition. These are transition probabilities of states of mastery over time. So if the longitudinal data that are being collected are collecting not only continuous data, but state data, one can examine changes in states of mastery over a particular period of time, which is a different way of conceptualizing growth. It's movement in probability from one mastery state, or failure state perhaps, to a mastery state as well. So the opportunities are myriad in terms of the statistical models that currently exist, the software that currently exists for doing this. It's simply a matter of the data. So what are the challenges in building longitudinal data files? Well, we're going to consider really one in the interest of time, file matching. And as I will say, as I said earlier, the issue on privacy, I think I will pass both in the interest of time and secondly because I think it's going to be covered quite well by others in this seminar. The question is, can we combine data from various sources to provide a richer set of variables for research and policy analysis? This problem is more or less straightforward depending on the level of aggregation. The short answer to the question is yes, of course you can. The question is, what is the nature of that database when you're finished merging these files together? An example, additional country-level data from the OECD can be added to PISA country-level data for the purposes of studying cross-country growth. That is to say, the OECD has national data apart from what's measured in PISA that can always be added to a study in PISA, right? Just get the OECD data for Israel. What we're talking about here is creating synthetic longitudinal data, and this has been done in the United States. We've had a study called the Early Childhood Longitudinal Study Birth Cohort added to the Early Childhood Longitudinal Study Kindergarten Cohort. They're not the same kids. So when we're talking about file matching, what you're talking about is creating synthetic data. They're not necessarily from the same children, or schools, unless you're fortunate enough to have complete census data. You're matching data from different sources. Matching individuals from different databases requires sufficient background information for the match. That is to say, it's very useful to have sets of data in these different databases that are the same. Okay? Statistical methods are needed to check the validity of the match. It's not simply a case of whether you can do it. You can. The question is whether or not the approaches for matching, which often involve imputation of the missing data, are valid. That is to say, if you have data from two different files from two different people, basically you have a massive missing data problem on your hands. Namely, people in one file were not participating in the data collection of the other file. So if you're going to create a synthetic database, that is a missing data problem, a massive missing data problem, and it's missing to a great extent by design. When matching files together, one has to be knowledgeable of the super exogenous changes in the policy context. That is to say, matching databases often means matching databases that were collected at different points of time. And if there had been super exogenous changes to the context, when these data are matched together, it's not entirely clear what that population is that you are referring to anymore. So thought has to be given to the population that the synthetic cohort now represents. You're creating a synthetic cohort. It's representing some population. Is it the population you wish it to, in fact, be measuring? That has to be taken into account. I should also point out that it's not a simple matter of imputing the missing data. As it turns out, imputation methods there's quite a lot of them. There's quite a long list of imputation methods, and myself and other people have studied them. This is just a list of 6 of the different imputation methods. So a choice needs to be made if you're going to then create a synthetic cohort of data in which you are going to now impute the missing data. Which missing data mechanism are you going to, which missing data program are you going to use? These all exist. It's not difficult from a technical point of view to do it, but these will all give you slightly different results. So a choice has to be made with regard to the imputation method that's being used to create the synthetic data. Moreover, for any rigorous data fusion, which is one way to refer to this, validity criteria must be established. Now, it turns out there's some very good work being done on this topic, and have been done on this topic by Susanna Rossler and her colleagues. And she talks about 4 levels of validity in putting together a statistical file that's matched from different sources. The first level of validity is preserving individual values. That is to say, actually somehow providing the value that you would have answered had you taken that particular survey. She indicates that that's probably not reasonable to really reproduce exactly the kind of values that a person would have gotten. The second level of validity is to preserve joint distributions among the variables that are in the data set. The third level of validity, very important for statistical modeling, is to preserve correlations and covariances. And the fourth level of validity is to preserve marginal distributions, which is minimal. You have to preserve the marginal distributions. So we tried this in a study based on fusing or data matching Thales and Pisa, and we used data from Iceland. The reason we used data from Iceland, Little Iceland, is because they did basically a census of Thales and Pisa. So what we could do is we could fuse them together because we knew what their answers already were. So that what we would then do is take the total Thales and Pisa data and then remove data as though they didn't take both surveys in their totality, and then see if we could reproduce the marginal distributions of the data. That way we could check the validity of the imputation, the validity of the matches, and look at various different procedures. Well, cutting to the chase, this is a little bit hard to see. This is optimistic, as you might say, for those of us. But basically what we find is that the solid line represents the imputed data, and the dotted lines represent the original data, because there wasn't any need to create missing data. Iceland measured everything. And what we find is that one of the particular methods that we looked at for imputation did an extraordinary job of reproducing the data, the marginal distributions of the data we already knew. The point of this is that this is a validity test for imputing missing data in a file matching situation. So if you're file matching, and if you decide to impute in order to create administrative data that looks complete, then what you have to do is be sure that you've chosen the right imputation method and validate it somehow. Come out with some way of validating this thing so that the choice is made on the basis of reasonable reproduction of the known marginal distributions. What are some of the challenges with this data fusion? Things that we have not quite worked out yet. Well, we have to deal with multi-level problems because kids are nested in schools. So you're going to fuse data sets for education. You're going to fuse data of children nested in schools with other kinds of data. This is a fusion of multi-level data, and this is not trivial. We need to deal with the sampling weights that are different for different administrative data, different for different kinds of data that are being collected. How are they going to be handled? Because they need to be dealt with in a very careful fashion so that one is making inferences to the right population. And then what I mentioned earlier are the temporal concerns we need to take into account, namely the fact that some of these administrative data collections were collected at different times. And so if there are any super exogenous changes to the Israeli context during those periods of time, it's not entirely clear that that administrative fused data set represents any population that one could reasonably imagine. What are the opportunities with data fusion? Well, cost savings. So administrative data, as pointed out in some of the documents you gave me to read, is that there's great cost savings involved in doing something like this. Greater coordination and collaboration in national data collection efforts could be an advantage to the use of administrative data. And of course, there's potential for great policy relevance, particularly when the data files are matched with other national system indicators. Okay, skipping with the privacy. Let me talk for one more minute, a couple more minutes for the extended opportunities. The challenges of mounting a longitudinal study and providing the data data for longitudinal studies are real and they are serious. However, the depth of what can be learned makes the effort worthwhile. So what are the other extensions that we can actually look at beyond what we saw? Well, large-scale cross-sectional and longitudinal surveys cannot measure every interesting variable. We can build rotation designs to do this in order to deal with not administering every single item. But perhaps it's better to start thinking about these surveys as measures of important indicators of the health of national educational systems, particularly if no new data collection is going to take place. So what are the characteristics of these indicator systems? Well, first, they should be theoretically or empirically linked to other indicators. They should serve to monitor real or simulated changes in outcomes of interest. They should act as proxies to real policy instruments. And they should be validated in terms of whether or not they are moving in relationship to other movements of indicators when such movements are presumed. We can use these indicator systems for policy purposes, and in particular, I would argue, we can use them for forecasting and prediction. But if the interest centers on forecasting prediction, then adherence to one's idiosyncratic theoretical model is less important and in fact counterproductive than focusing on combining many possible models to obtain optimal prediction. So one of the areas of interest that I have is this notion of combining models to obtain optimal prediction. So assuming you have already your administrative data in hand, that you've created a longitudinal data file, one of the things that we can do is think about using those kinds of data files for forecasting and prediction, in which case theoretical models are less useful than combining or averaging over a large set of models. A key characteristic of statistics is to develop accurate predictive models for forecasting purposes. Prediction and forecasting models can then be calibrated based on the accuracy of their predicted outcome. As you are beginning to look at these models in a predictive point of view, their accuracy, if you will, is based on how they did in terms of forecasting outcomes in education that one may be interested in. For Israel, matching data files should be done with an eye toward which indicators are needed for policy purposes and predictive modeling. And this is something that our research group is doing, but I will not spend too much time talking about this. Anyway, thank you very much, and that's the end of my